Hi, and welcome to SP Live and today's discussion on innovations in produced water management in oil and gas operations. My name is Nils Korgensen-Low. It's my great pleasure to be your host for today. If you're new to SP Live, check us out on social media, hashtag SP Live, or find us on spe.org. Now, we have another really fun-packed week of SP Lives. This Thursday, subsea technology innovations, tiebacks versus FPSOs and flow assurance. And Sunday, we're very honored to have Reem Al Gahaim, head of HR Support Services Chemical Division, Saudi Aramco, in our Middle East studio, talking about gender and global diversity in the energy industry. Now, all content available on demand for free. SPE Live is in part made possible by sponsorship from the SPE Foundation. If you want your name, face, and brand associated with the mission of SPE and the SPE Foundation, well, we have over tens of thousands of followers. So if you want to sponsor SPE Live, please contact us on spelive@spe.org. We are waiting to hear from you. We are busy booking our 2021 program schedule as we speak. So first come, first serve. Please join us as SPE Live sponsors. Today's SPE Live is our continuing journey on technology innovations, addressing operational challenges in our industry. In this case, produced water, and more specifically, produced water in unconventional operations. Produced water is not an unknown or unusual occurrence. Offshore and land operations often differ in the way water is treated and disposed of. In most cases, the produced water is saline, salty, making disposal for land operations in particular more challenging. For unconventional operations, the volume of produced water is cumulatively extremely large, and due to the very high intensity of the operations and very large number of wells. So the challenge of managing produced water in these unconventional operations falls into this gray area between upstream and midstream operations. So it's not the most common discussion topic for petroleum engineers, yet it should be, as it directly impacts our environmental footprint. Now, many of you watching and listening know produced water management. You deal with it every day, offshore and onshore. So please share your comments, thoughts, questions. We want to hear from you. Now, joining us today to talk about some of the operational challenges and innovations in produced water management is Dean Fangu, Director of Business Development, Western Hemisphere for Tetra Technologies. Dean's primary focus is expanding the application of Tetra fluid management technologies and solutions. Prior to joining Tetra, he was the Director of Sales and Marketing for Tavita US, a diversified environmental services provider. He has served also in various global business development, sales and marketing and operations leadership roles with Baker Hughes during a 30-year career. Dean has authored publications on various well completion and intervention techniques, including multi-stage hydraulic fracturing. Dean, welcome to SP Live.
Hi, good morning, Nils. Thanks for having me today.
You are very welcome. We are talking produced water management and innovations in technology, in particular challenges facing unconventionals. Just a quick reminder to our audience, please share your thoughts and comments and questions. We will be watching and listening to your comments as they come in and hopefully using your questions as we go. So Dean, produced water, unconventionals, but also conventionals. Let's, for a moment, start off with what are some of the drivers in produced water. So give us a sort of scene setting around the drivers for produced water management.
Yeah, so, water obviously is produced at much higher volumes than oil. In fact, a lot of oil companies have often admitted that we're really almost really a water company because of the extreme volumes that they have to handle. And this goes for not only the unconventionals, but more so on the conventional side. A lot of our oil reservoirs around the world conventionally are water drive. So that water pushes the oil out. Now, obviously in the conventional market where you're not doing hydraulic fracturing, you're not really using the water as part of your completion program. But as we've seen in the unconventionals, we're using, billions of barrels of water to actually create the hydraulic fracturing and using it as a conduit to get the sand down hole. So, managing produced water in the unconventionals is critical to the success in the future of well completions.
Yeah, absolutely. And you touched on it there. Just for the audience, sort of information, what kind of volumes are we talking about, in produced water in unconventionals, for example?
So thinking about the demand of water as a whole for unconventionals, in 2020, we're looking at about 3.5 billion barrels of water as a whole. Now, produced water has more commonly been used in taking share from historical use of fresh water, water that would come from the surface or subsurface. And now, obviously, the realization that we can take produced water, minimally treat it, and use it for fracturing. And obviously, the water that came out of the reservoir is good to go back into it. And there's also been concerns over time about high percentage of fresh water potentially causing shale swelling. So the produced water and the blended fresh water, which is the most common recipe for fracturing, is certainly growing. And we have some basins in the U.S. where there's some restrictions on disposing of produced water, such as the Appalachia Basin, and they reuse 97 to 98% of all of their produced water on an annual basis. Whereas in the Permian, the amount of produced water that's being used is growing, but it's still maybe around 30% of the total volume that's produced.
Okay, so very interesting numbers there, Dean. So thank you. So you're saying the Appalachians, they use about nearly 100% of their produced water is reused, lower in the Permian. Now you mentioned 3.5 billion barrels is used in 2020 or in 2019, right? I guess if we go back to the previous activity peak, that is for completions, or is that in the total volume of water produced?
So that 3.5 billion is the frac water demand, the total frac water demand, both fresh and produced.
Yeah. Okay. So I mean, the produced water content is much higher, right? So I think some numbers batted around is that the daily water production in the Permian is 450 million gallons a day, which is the equivalent of the city the size of Houston in terms of its water consumption. So very, very large volumes. So we're talking very large volumes, which sets apart the unconventionals from the conventionals by and large, partly because of just the huge number of wells and the huge amount of water produced. So it's seen as a waste stream, so it's a cost. Talk us through some of those challenges around, the drivers and the costs related to this waste water.
Right. So, typically, historically, operators, as part of their production operation, they'll have the co-produced water that comes out with the hydrocarbons, and then they have to take that water to disposal if they're not going to reuse it for hydraulic fracturing. And, water in some areas where disposal is not available, because there are some areas where there aren't enough disposal wells or any disposal wells, and it could cost as much as $9 a barrel to take that water, transport it, and dispose of it. But more commonly, where you do have quite a bit of disposal infrastructure, you could still spend $1.50 to truck and dispose of water. So the cost per barrel can be quite high, whereby reusing and recycling the water can be much lower. Especially if the water is already in the production system and readily available.
Yeah, absolutely. Yeah, just what you're saying there, in just terms of that cost saving, in terms of not having to move all this water around. I think we actually have a really cool video from you guys that we can show, just to sort of give the audience an appreciation of the scale of these kind of operations. So this is what a water impoundment, right? So we're seeing you guys walking over the bund here, and as we zoom back, I mean, to the audience, this is just amazing. The size of these impoundments gives you an impression of how much water is being stored and recycled, right? So
Yeah.
Very large. So, Dean, you talked about the infrastructure. Maybe we can get into that. Again, that's something that sets apart unconventionals from conventionals, largely, again, because of the volume of the water. So let's take the Permian or Appalachia, for example. What's the sort of infrastructure that's in place or needs to be in place to make this kind of thing work properly?
Right. So for recycling or reusing produced water for hydraulic fracturing, what you'll need is a buffer storage area where you can bring in raw produced water. You can have readily available produced water to treat, and then move that water into a large in-ground impoundment, such as what you just saw. In fact, the impoundment that was on the north side that you actually had liquid in, that was clean, produced water with an aeration system in place to eliminate or prevent biocidal growth. The pit to the front was for future storage as volumes increase.
Yeah. Okay.
And again, to make it really economical, as in cases where you already have produced water facilities nearby where you're going to be performing hydraulic fracturing, and you can just have a continuous pipe going to the recycling site, and then from the recycling site distributing that water to frac sites, what we call a hub and spoke operation. But we also do quite a bit of on-pad recycling, where a well pad is near a produced water handling facility, and we'll actually put the recycling site adjacent to where the hydraulic fracturing location is.
Yeah, so that really addresses that issue where we produce water where we don't want it necessarily, or always, and then where we do need it, we don't actually have a lot of water. So as you mentioned earlier, we have to often use fresh water from freshwater wells rather than being able to recycle. So that infrastructure is important. Now, I think one of the sort of innovations I've noticed over the many years that the Permian has evolved, and as with many other the US unconventionals, is this development of the midstream infrastructure. So you mentioned how you have these, we'll talk more in detail about these sort of the water treatment facilities that you guys have. How do they sort of tie in with sort of the midstream infrastructure that we see growing up around these unconventional operations?
Yeah, no, that's a good question. So both on the operator side, so operators, oil and gas operators, especially where they have a lot of contiguous acreage, they have their own water midstream lines. And, in that case, or in the case of a commercial operation where it's a company that has maybe acquired an operator's water midstream assets and will operate those for the operator, and also share that water with other operators, or aggregate water between operators, we can set up recycling sites along the midstream pipelines, the water pipelines that take the water from the different producing facilities at the different well pads, and they bring those into a centralized facility. Well, that water can be shipped back out to the emerging development areas and near those frac pads. And most pipelines, midstream water pipelines, have risers about every mile. So we can connect to those risers wherever there's a frac location nearby, and we can actually set up a recycling site in that vicinity and then distribute the water back out to the fracs.
Yeah, absolutely. So again, it's that midstream piece, and as you say, the infrastructure. So maybe do you want to comment a bit about, why is there a midstream business in some states, for example, around unconventionals, whereas it's not in other states? Is that a difference between how wastewater is regulated, who owns it, who can trade it? Is it a commodity? Is it just a waste product, a byproduct? What's your thoughts?
Yeah, so every state today has a water midstream entity. It may be with an entity that's owned by an operator, or it may be a commercial entity that's, privately or publicly held, and they're servicing one or more operators with that infrastructure. But we now have progressed in the U.S. I believe every state now has water midstream. I mean, whether it's owned by an operator or a commercial entity, there's water midstream infrastructure in every state.
Okay, so that's a really positive step forward in terms of our environmental footprint. Before we talk details on some of the water treatment, given your international experience, and we have an international audience, so there's probably a lot of people scratching their heads thinking, how does this apply to the Middle East, for example, or other locations? What can you say about the sort of the applicability of your type of infrastructure and other infrastructure that we see here in the United States with unconventionals? How does that work, or would it work in other locations, do you think, like the Middle East?
So today, we have ongoing shale development in Argentina, in the Middle East, especially in Saudi Arabia. We're going to see unconventionals begin development again in restarting those on some pilot projects in Colombia. And with regards to the water infrastructure and the way that water is handled in the US and Canada today, which is very similar, the Middle East, Argentina, Colombia, they all have the same opportunity, and they're already recycling water. They've recycled water in Argentina. They don't have nearly as much midstream infrastructure built yet, but they're moving in that direction because there are areas in the Vaca Muerta that has a more arid area where there's less fresh water available. And so we understand that they intend to recycle produced water, which will involve putting in produced water midstream lines. In Saudi Arabia, they're mainly using a lot of seawater, and so they have water, you could call it water midstream lines that run from the sea and run inland into the desert where the hydraulic fracturing is taking place. But it's mainly freshwater infrastructure today.
Okay, so that's another important differentiation.
Or I should say, I'm sorry, I should say, I need to correct myself. I shouldn't really say freshwater. It's actually seawater that's been desalinated.
Yeah, okay. So, but I mean, we'll talk a little bit more about this in a minute in terms of the salinity of the water and the treatment, but maybe it's worthwhile pointing out that even seawater needs to be treated before it gets used, either desalinated or treated otherwise before it can be used as a frac fluid. So, water treatment is still an essential piece to the puzzle. And water treatment, some old technologies, we've had produced water for years, we've used water for years in operations, so it's not new technology. If we can, let's just switch our attention to what are some of the innovations around water treatment. You guys have some really neat technologies, I think. So maybe start with sort of high level, and we can start going through maybe some of the details of what a typical water treatment facility looks like and the innovations that are now here in the marketplace.
Yeah. So the first thing is we've recognized that, as I mentioned earlier, we don't need, if we're going to reuse produced water, we don't need to treat the water to a distilled level. The chloride content is quite beneficial to the formation or to the reservoir. Again, that water came out of that reservoir. If it goes back in without any of the scale forming solids, with no bacterial growth, that water is very suitable. And if the chloride content is too high to mix with the frac chemistry, and it creates too much friction to pump the frac, then we obviously dilute it and can dilute it with fresh water. And that's very common. The most common blend today of frac fluid is treated produced water blended with fresh water. The only area in the US where we're not really using a lot of produced water is in the Williston Basin or the Bakken Shale Formation. And that's mainly because the chloride levels are extremely high. They're over 200,000, around 200,000 parts per million. And they do have a lot of fresh water available, and they have a lot of disposal infrastructure there as well. But everywhere else, we're blending produced and fresh water. In terms of the basic treatment, today, most companies that are recycling water are just really looking, as I mentioned, to remove the scale-forming solids such as iron. We're not really looking to soften the water, so we're not touching the calcium. We're basically treating the produced water with an oxidizer, which works really well to treat the iron, to treat sulfides, to treat the bacteria that may exist. And then we put in a coagulant to get the solids to come together. And then we put in a flocculant to flock the solids out. Some people refer to it as flock and drop. In our technology, we like to flock and float. What we do is basically take the solids to the surface of the clean water, and then we're able to skim those solids off, keep them in solution, and actually take those solids to a subsurface disposal well. So there is some disposal that takes place, but it's an extremely small percentage compared to what they were disposing before. And what you end up with at the end is an incredibly clean and clear produced water.
Yeah.
Now,
absolutely. Yeah.
Lastly, if we're using treated produced water, and whether we're using fresh water or not, before we actually get to the frac, and just before the frac, is where we also provide another treatment for bacteria, because in the warm climates, bacteria growth can form very quickly, and so you want to make sure that you have no biocidal growth in that water before you frack with it. Otherwise, you could end up with some souring after the well's completed.
Absolutely. And I think we have another video that we can sort of talk through just to show people, you talked about the high level treatment technologies. So if we bring up that other video, you can sort of talk us through, this is what a typical site would look like. So talk us through what these different elements are as we zoom in.
Right. So in the first scene here, you'll see a blue, or originally it was a black hose. You can see the water flowing through it, going through a pump. That's where we're bringing water from a freshwater location using a high horsepower pump, which is automated. I'll come back to that in a moment. What we have here is a treatment system that eliminates the bacterial growth just before the frac. So if we're doing just a freshwater frac, we're moving fresh water directly to the treatment system, which in this case, we're using chlorine dioxide, which is the most common biocide used in the world. In fact, many municipal water plants use it. So it's very safe and it's very effective. And so now what we're looking at is a blending and distribution system if we have produced and fresh water. So you can see that to the right side, towards the top of the screen, you have produced water that's treated coming in one side of the blender, and then you have fresh water on the lower side. These can be brought through either using measuring the chloride content and adjusting the percentages, or you can use just ratios of water. It's a very accurate blending system, and it does blend on the fly. Now, prior to that, we have our water recycling system, which I discussed earlier. We currently have projects with a system like you see here that are treating 100,000 barrels a day, okay? So we can scale them up or scale them down. We have some projects where we're only recycling 12,000 barrels a day. So these are very modular systems. They all use the same state-of-the-art technology. We have real-time monitoring and control through all of the touch points on the water. We're able to have our operators log in and actually see everything that's going on with their water. Now, one of the technologies we developed as a result of a large-scale recycling project several years ago was where we were getting a lot of produced water coming to the recycling facility where the oil hadn't been removed. And what was happening is they were developing this field at a rapid pace, and their produced water gravity separation system wasn't taking the oil out fast enough. So we had to create a system to speed up the retention time or minimize it, where we're able to remove the oil in advance of the water, produced water going into the recycling phase. So we were able to return to that particular operator 84,000 barrels of oil, which they were able to put back in their sales line. Now, once we go through the produced water recycling phase, blending it with fresh water, treating it with a biocide, and then fracking with it, we now have to deal, once we've completed with the well and it's been fracked, we need to flow back the frack plug remnants as well as some of the frack sand that was in the well bore. And one of the innovations that we developed was sand management technology that could handle even the very fine sands that we're now using a lot in field. So we're now using in basin sands, 100 to 200 microns. Obviously, after those sands are pumped down whole, they obviously crush. And so we needed a new technology and a different way to recover sand on the flowback, because original sand management, sand separation technology was designed to remove larger proppant sands, 70 microns and below, as well as ceramic proppants, which had very little crush. So now we had to change the way we were recovering sand. And fortunately, now we have the technology. We just finished a project where the well was flowing at 45 MCF a day, and we recovered 99.4% of the sand coming out of that well bore.
Okay, so that's like a sort of typical layout here that we can see. I think one of the things that you talked about was the automation piece around
Right.
this. I mean, this has been one of the big innovations, is automating these various processes, integrating them, having fewer personnel in the field, so obviously improving site safety a lot.
If we could pause here.
Yeah, sure.
I'm not sure if you could pause or go back just a little bit to show the full view, just to provide those participating in the call today with a sense of, some benefits to the automation that the automation brings. So when we look at this picture or this illustration, this is what we would call an integrated water management project, where, from the time we take fresh water from the surface or subsurface, where we may be also bringing in and treating and recycling produced water, where we frack with this water, and then we flow it back and bring it back into the system, and then bring it into the next project, right? So it's really a closed loop environment, truly closed loop environment. Well, by having all of these components automated, if we look at a typical project and the number of personnel that would be required to provide the functions manually, excluding the fracking itself. So, outside of the pressure pumping piece, but personnel in a 12-hour period to manage all of these pieces of equipment, it would take 28 people, okay? We can do that now with less than half as a result of having real-time monitoring control. So the cost savings are tremendous. By removing more than half of the personnel, that provides less concerns on QHS&E, less trucks and vehicles on the road, and better utilization of personnel, because now the people that are involved with the project are learning another skill level. It's basically elevating their career by having them working with real-time monitoring and control, as opposed to manually operating a pump, for example.
Yeah, and absolutely there. So just to, for people's benefit here, so this site here is highly customizable, right? So, you know, we can,
correct,
you can take components of this and apply it elsewhere. So a couple of questions we had from the audience. Someone was mentioning produced water is usually saltier than seawater. Why do we then need to desalinate seawater? Do you want to sort of have a go at answering that?
Correct. Now, the seawater wouldn't necessarily need to be desalinated, but you know, it would need to be compatible with the formation, depending on, you know, the design of the frac. So the seawater can be cleaned without desalinating it. If there is fresh water available, you could even dilute it. But in most cases where you're going to be using seawater, you're using it because you don't have very much fresh water, if any, available.
Yeah, exactly. And we'll talk a little bit more about some of the, I guess, the salinity of the completion fluids, you know, because I mean, there are some very saline completion fluids being used at the moment. Related to the completion fluid, Rediat Mogoes on LinkedIn was asking, what's the maximum chloride level that is deemed okay in completion or drilling fluids? So, you know, that's on a case-by-case basis, right? Correct. Depending on the bacteria levels.
Right. Well, today we're using 150 parts per million TDS water for hydraulic fracturing. Now that water is diluted by probably 50% okay, or maybe even 60%, where we may be using 60% fresh water and 40% produced water. Obviously, if the chloride level is lower, down to the 70 thousand parts per million, then we obviously don't need as much, necessarily as much fresh water. On the drilling side, I can't really comment on that. I've been away from that for quite a long time, but that's a great question. And, so we're mainly in the unconventionals today. A lot of the surface holes are being drilled with air now. So they're not doing nearly as much water-based drilling, and they're using oil-based mud in the horizontal section, so or an invert mud. So the freshwater volume that's used for drilling in the unconventional is quite low.
Yeah, I mean, that oil-based mud usage may change if oil prices ever go sky high again, because I mean, there was that move 2017, 16, when high oil prices and people started moving to water-based drilling fluids. Going back to that integrated spread that we saw earlier. So obviously that's a land operation. It's the video, the images for an unconventional type of operation. So if you were using seawater, you can imagine that you're drawing water in from the sea. What components, if any, can be used for conventional offshore operations, for example, where you're taking seawater, you still need to treat it, and maybe you're gonna pump it back down into the reservoir, or even use the seawater for like cuttings reinjection. Can you take components of that system and use it in other kind of scenarios?
Yeah, interesting enough, we actually took some of the offshore treating technology and brought it to the onshore area. And the reason why is because our industry has had a much longer history of treating water offshore from conventional wells. And so, for example, one of the common technologies that's been adopted in unconventionals as part of the water recycling process is a dissolved air flotation device, which actually really enhances the ability to remove the any remaining hydrocarbons from the produced water, as well as the flocked, coagulated and flocked solids. We've taken that to another level in our offering with our technology, but the base technology came from the offshore industry. We also use some polishing filtration technology on the back end before we released the treated produced water to the frac. And that technology came also from the offshore water treatment space. And a lot of the biocides that are being used in the unconventionals for biocidal control came originally from the conventional water treatment and offshore water treatment applications.
Okay, and like you say, you transfer the technology from offshore to onshore, and there's nothing to stop you from taking the same innovations and taking them back offshore, right?
Correct.
So have an automated system offshore or
Correct.
in another location. Just another couple of audience questions here. So again, Aradiat Magoes on LinkedIn, impressive automation innovation technology. Will biocide be a continuous or batch treatment in this type of setup?
Mm-hmm.
What is it typically?
Yeah, so that's really a good question, and it really can depend upon how long you intend to store your water before you're going to use it. You may want to put some biocide into your pits or ponds or containment areas. You may be using above ground storage containment. And depending on the climate, you could put biocide in there. We're using aeration systems, which are incredibly effective. And most of the water that we're recycling and most of the fresh water that we're temporarily storing before the frac is not sitting still for very long in one place. And so we typically mainly treat the water when we get to the frac, right before the frac. That's the most effective use of the biocide.
Yeah. And just one more comment from the audience. So JJ1266 on YouTube said to good mornings earlier, question about the seawater treatment. So yeah, there's the sulfates that you need to knock out from the seawater because it's not compatible with the formation always. So to everybody in the audience, always check your produced water or whatever seawater you're going to use and inject into your reservoir to make sure it's compatible with your reservoir before you inject it. So that's always a good lesson there. Now, Dean, we've been talking a little bit about the salinity of the water. And traditionally, in completion technology, we've used fresh water for completion fluids. That's obviously changed over time, particularly in the unconventionals. Talk to us a little bit about slick water and the salinity of slick water and some of the innovations there now that we see.
Yeah, that's a great subject. We, again, it goes back to the industry when we first started modern day hydraulic fracturing, and I say modern day back 15 or so years ago. We still thought in some cases we needed distilled water to frac with because at the time the frac chemistry wasn't capable of reducing friction if you were to use higher density fluids such as produced water. And so we were using cross-linked gels most commonly, or a hybrid gel system, when we started to use produced water. And then, the cost was extremely high for these gels and the volume of gels that were being used. So operators put a lot of pressure on the service companies to really, work in their R&D labs to come up with technology that would allow us to use, you could say dirtier produced water, meaning produced water where you weren't softening it, but produced water where you just, made it clean enough to where you weren't going to have scaling or fouling issues once you pumped it. And so the evolution of high viscosity friction reducers came about, and today there are many different types of high viscosity friction reducers that are being used. And what that's allowed us to do is evolve from where we were doing, maybe 6-7 years ago, only 20% of all fracs may have been slick water fracs. Today, it's about 80%. So, slick water fracturing today is by far the most common method. And that is a testament to the innovation in the high viscosity friction reducers, which also have lowered chemical costs significantly and made
Yeah.
these unconventionals a lot more economic.
Yeah, I mean, that's a big, as you say, a very big positive step change. And it also allows us to use that more saline produced water, right? Correct?
Yeah, absolutely. Yeah. And to that point, as I mentioned earlier, we're now using some extremely high TDS waters. Obviously, when we get into the 150,000 parts per million range, we're diluting the water, but it would have been very difficult for us to have used that type of mixture without the high viscosity friction reducers.
Yeah, absolutely. So that actually brings us to like the next talking point, I guess. We're talking about the salinity of the water, the high TDS. So it's always been a big challenge, particularly in the unconventionals with this very saline formation waters. So looking ahead, what's the future look like? I mean, we use a fraction of the volume of the water in the completion fluids in unconventionals. We have this vast volume that still has to be disposed of. So talk us through a little bit about the future in terms of disposal and treatment of the additional volume of water that we have in our operations.
Yeah, so we're going to continue to have situations where operators may not have a frac schedule and they're not able to recycle water, but yet their production is growing. Now, as these shale wells, the longer they produce, you do get a decline on the water production as well. Initially, when you flow the well back, you get some pretty high volumes, but then that starts to decline over time. And these unconventional wells, you don't have as high a water cut as I mentioned earlier as a conventional well. That's the reservoir is really around the water pushing the oil out. So on the unconventionals, you have to have a strategy as an operator to know what your infrastructure, how does it need to be sized. How can I handle the produced water when I'm not going to be able to recycle it? Where the commercial water midstream has grown, the concept, and we have some incredibly large commercial water midstream companies now, especially in the Permian Basin, is they were able to help operators by taking care of their produced water infrastructure and being able to create almost a co-op between multiple operators, so that when one operator maybe was just needing to dispose of water, another operator needed more water to frack with. And so by sharing water between operators, it creates a lot more flexibility when you have these times where you're either constrained on adding more completions and you don't have the ability to reuse your water, and you have to dispose of more water. And so, but we also have to think about beyond that, because we are seeing in some areas seismic activity. We're seeing some regulations in some areas where the amount of allowable injection pressure based on volume is being reduced and restricted. We have to find another method of using produced water or getting rid of it. And so there's been a lot of innovation in the water treatment and water management industry focused on more affordable and economic recycling or treatment of produced water to where it can be discharged on the surface or reused beneficially, whether it's maybe agriculture or maybe in cooling towers in power plants or industrial usage, as opposed to disposing it. We also have some technologies that have become economic to actually just evaporate the water. And the more economical technologies use waste heat that already exist in the field of operation near where the water is being produced. So for example, one of the companies that we're working with actually is using waste heat off of centralized gas compression facilities and using that heat to help in the brine concentration and evaporation process. And so, you know, the whole strategy here is brine reduction or finding a beneficial reuse.
Yeah, absolutely. And you've touched on some really important points there, is that brine reduction. So you mentioned evaporation or beneficial reuse. So, you know, with the brine reduction, as you also mentioned, there are, like in many locations, particularly Oklahoma is one good example, where there are limitations on how much water can be re-injected into disposal wells. So, you know, obviously concentrating the volume of water through evaporation helps reduce the injection volumes. What about sort of other desalinization? I'm thinking here, you know, there are some significant advances now in electrolysis coming up, you know, that we're seeing in the headlines and in the news about desalinization being powered by solar or even wind. You know, you expecting anything big changes coming up there that can be really beneficial in desalinating produced waters?
Yeah, I mean, it's amazing, the emerging technologies or the green technologies that are emerging. We're seeing tremendous growth in wind power. You know, there's some studies out there that, you know, a lot of us were somewhat pessimist and you know, had a hard time understanding, you know, exactly how much solar or wind could replace oil consumption or natural gas use. But those technologies have come a long way and are expanding. And yes, some of those technologies may be definitely a part of helping us take produced water and turning it into a beneficial product outside of using it for hydraulic fracturing.
Yeah, absolutely. You know, for me, one of my big hopes for our industry is, I'm just thinking now of Texas and the Permian. Texas out west is very arid and dry. We have a lot of salty water. To me, the hope would be that we could take that salty water, desalinate it, and use it for agriculture, right? You know, we have lots of sun, we have lots of wind power out there. So that would be, to me, a dream come true. I'm just going to turn a little bit to a couple of questions that are related. So Temitope Adebanjo on LinkedIn was asking, what are the most important controls during the recycling process? That comes down to cost application. And Steve Coffey on YouTube, he was asking, what are you seeing for produced water treatment costs and all-in costs when it comes to, for example, US shale plays? So you mentioned the cost a bit earlier. What are typical cost ranges that we're seeing in these kind of processes?
Yeah, well, obviously, the larger volume of water that you can, if we're talking about just recycling the water, okay, just taking produced water and recycling it to a point to where it can be used for hydraulic fracturing, this wouldn't necessarily include the biocide treatment. The biocide treatment is incredibly low on the per barrel cost. I mean, it's in the pennies. But also on the recycling side, so the more volume you have, the more you dilute your fixed costs, no pun intended. But, you know, we see 100,000 barrel a day recycling centers that are, you know, the cost can be, you know, easily below 50 cents per barrel. And it can be, you know, as low as, you know, probably, you know, 30 cents or a little below 30 cents. It just depends also on the operator's specification on what they want the effluent water to be versus what the original water quality is before you treat it. Because a big part of your recycling cost is the chemical use. And so you know, 100,000 barrel water recycling facility, we can actually do it with one person on a 12-hour shift. Now, we're not doing that only because where we're recycling, where these recycling centers are, they're fairly remote areas. And for safety reasons, you need to have a couple of people out there to ensure that, you know, if someone, you know, has an incident or becomes ill, whatever, you know, you have to have a backup. But with our automation systems, it's amazing how much we've reduced the cost on the personnel. And we've also reduced fuel costs tremendously because our pumps are running at optimum speeds at all times.
Yeah, great to hear that, Dean. So, again, it's just how the power of our industry is sort of just innovating, reducing costs, becoming more efficient, and particularly for around what is a waste product. And you mentioned before the beneficial use of that waste product, in this case, water. So very exciting to hear all these innovations. You talked us through some of the technologies, the drivers behind water treatment and water management. So thank you very much for bringing that to our attention today. Any last thoughts, looking ahead again to the future? What else, what would be a sort of a closing remark to the audience from you, Dean?
Well, again, I think it goes back to the point you made earlier, Niels, that, we've got to continue to look for ways to lower the cost of oil and gas production, development and production. We've got to compete with, in the marketplace. We've got to be able to demonstrate that we can work safely and have minimal impact on the environment. And so I think, continuing to focus on lowering the cost per barrel of reusing produced water, lowering the cost per barrel of taking produced water and cleaning it for beneficial reuse will go a long way in the environmental stewardship, but also to continue to make oil and gas operations economic.
Yeah, absolutely. Thanks, Dean. That's fabulous to hear that. And thank you for all your insight today. It's been great sharing this last 50 minutes talking to you about water management. So thank you very much for your time today and joining us here on SPE Live.
Yeah, and thank you and the audience. It's been fantastic. Really enjoy the collaboration and look forward to the future. And thanks again for having us. We really appreciate it.
Oh, you're very welcome. It's great to have you here on the show. So thank you. So that's our wrap, guys. So thank you to Dean again. Thank you, audience. You're marvelous as ever with all your questions and comments. To all you asking about jobs and looking for jobs, I see you out there. I can see your comments. I do sympathize with you. Go to the SPE.org. There is a job board there. So have a look at that. And also there's many other commercial job boards that you should check out. There are jobs in the industry still. So go out and look and the best of luck to you all. More SP Lives coming up this week, so watch out for those. Check out our schedule. You can go to spe.org to find the schedule there, or you can find us on YouTube and LinkedIn on #SPE Live. Sunday this week, SPE Live looks at gender and global diversity in the energy industry with Saudi Aramco. That's going to be a really good show. This Thursday, SPE Live looks at early production systems, subsea tiebacks versus FPSOs, new technologies and innovations, and flow assurance. Thank you again, audience. Thank you, Asha, our producer, for an amazing show. Thank you, SPE Foundation, for making SPE Live possible through your sponsorship. We'll catch you all later, audience. Thank you very much, and see you later. Have a great day. Thanks. Bye.